some specific classes of theory, not the most general ones. And we're going to talk about, I'm going to talk about the correspondence. Separate connections from for the n equals to k series to each part of the correspondence. So that's the general idea. Of course, I'm going to focus more or less on this side of the correspondence, but I'll just from time to time mention this part. And also, I have to make a remark that I am going to use the QQ characters even before it is introduced. So it's a bit unfortunate. But maybe we can take it as a motivation why it can be useful and how we can get something useful from the QQ character. Okay, so let's start from which for the n equals 2 theory we are dealing with. So it's not just a random n equals 2 theory, but it is called class S, introduced by David Gaiotto. And it's classified by first thinking of 6-dimensional n equals 2,0 theory. And it is known that there's an AD classification. For my talk, we will restrict to type A n-1, A series. And moreover, for the simplicity, I will just take rank 1 case. Now, we compactify this 6-dimensional theory on the Riemann surface with possibility with some punctures, and then with topological twist to preserve some of the supersymmetry. Actually, this has 16 supercharges, real supercharges, and we are going to preserve 8 of them, making for the n equals 2 theory of class S. So this is called class S theories. And so to see why Hitchin moduli space or Hitchin integral system arises naturally in this context, it's convenient to further compactify on as S1 and look at the Coulomb branch of this theory. So in general, without this class S business, we know that once we compactify on a circle, the Coulomb moduli space has an integral structure with this and moreover, the moduli space is hyperkähler. What I mean by integral structure is that with one of the chosen complex structure, there's a 2,0 symplectic form, and we can view the full moduli space as certain complex tori fibration over some base. So here we have some moduli space. But for the case of the class S, we can reverse this order of the compactification. First compactify on S1, and we are going to get maximally supersymmetric gauge theory on 5D. That's n equals 2 in 5D. And then compactify on the Riemann surface. And we look at the BPS equation, what this moduli space becomes. And that actually turns out to be exactly the Hitchin's moduli space defined on the Riemann surface C. So let me remind you what this was. So MH is defined by the locus of set of equations by overall SUN gauge transformations, where here A is the SUN connection. So there's a SUN principal bundle defined on the Riemann surface C, and we think about the connection. And phi here is a 1,0 form with the adjoint values in the place principal bundle. And we divide by the SUN gauge transformations. And it's known that this space is hyperkähler. Right, and then for the simplest case, so our example will be 4-puncture sphere. So sphere with minus these punctures, 4 punctures. They are the position of the punctures. So this. And in this case, we know that, let's say, this is theory T. Then in this case, T is SU2 gauge theory with 4 fundamental hypermultiplets. Hypermultiplets. It's an n equals 2 it's a certain representation of n equals 2 superalgebra in 4 dimension. So it's some matter multiplets, as opposed to gauge multiplet. Okay. Now, the quantity there we are interested in the gauge theory side is the partition function of the gauge theory in the omega deformed R4. So we almost have seen it, but we were not quite there in the last lecture. So
here, the remnant 3 manifold is R3, or is up in the air, or you compactify down, you will compactify down something down to something.
Yeah, let's say R3. Let's say R3.
So it has to be R3.
Yeah. Okay. So for this gauge theory, what we are interested in is the partition function of the gauge theory defined on omega deformed. So I have to. So it is defined as a certain equivariant integral over the instant moduli space that we have seen. So it's a function of certain equivariant parameters. It has equivariant parameters for global gauge transformations, flavor symmetry, which has to do with these 4 fundamental hypers. And also, because if you think about the instantons in R4, it can just escape to the infinity if we don't do anything. So we have to properly regularize that singularity by turning on certain kind of potential which localizes the theory to the origin. So that has to do with the U1 to the square Cartan inside of SO4 isometry of the theory. So we turn on 2 equivariant parameter for that, epsilon 1, epsilon 2. And also we have the gauge coupling Q, which is, by the way, the same Q here. So this geometric data determines the gauge coupling. Well, this is certain partition function that was not introduced, but this is the quantity that we're interested in this gauge theory. So for example, when both epsilon 1 and epsilon 2 going to 0, it's proven by Nikita and Andre, and in other methods by others, that it has the asymptotic behavior like this. And this is exactly the Saebyeok potential, which governs the dynamics of the low energy effective theory of Pauli Anacostia theory. But actually, we are not taking this limit in this talk, but actually turning on. So we are taking certain less refined limit. So we're taking only epsilon 2 going to 0. And what happens is that some amount of a supersymmetry is not broken. Actually, some amount of the Poincare symmetry is broken by this epsilon 2. So we are now left with the two-dimensional theory, because one of the epsilon has to do with the U1 carton inside SO4. And actually, it turns out to be 2,2 super Poincare that's left, governed by effective twisted superpotential. The quantity that governs the dynamics of this effective theory is called twisted superpotential, and it can be exactly computed by taking this limit. So it goes like some living terms in epsilon 2. So
I thought these parameters would describe if you were on half four.
okay.
But you're compactifying on that. So doesn't that kill some?
Well, so let's forget about this. Then we can do this.
So you can, even if you compactify on a circle, you can still say.
Because we are left with R cross. Sorry.
I should forget about the circle.
It's, no. We can think about the circle. I mean, what's left is now circle times R then.
Yeah.
Yeah.
And so that is the effective setting epsilon.
Yeah. Yes. So yeah.
Also, while I'm asking questions, how do I know that there are no global anomalies?
I'm sorry.
That there are no global anomalies, that I don't have monodrome as I go around as I move Q around 0, 1.
Oh, I'm going to fix Q to be, yeah. I'm not going to vary Q. Yeah, there's some uncertainty that I don't want to talk about.
When you said that you think of Q as a gauge coupling,
Yeah.
so it's like you're appealing to some like other description of the theory somehow. Like, I mean, it doesn't look like a gauge coupling immediately when I just see it as like.
No, sorry, what's the question?
How do I see that Q is supposed to be a gauge coupling?
How do I see that? Yeah, it's the essence of the Gayoto's Anacostia duality paper, but one way to see that is sending Q to, for example, to another convergence domain corresponds to the S duality in the physics. But maybe that's the same way to say Q is the gauge coupling. So, yeah. Anyway, so now we have the gauge coupling Q, and we have this quantity which is exactly computable from the equivariant integral. Even though we haven't seen it, it can be done. So now we have to introduce a flat connections. Of course, it's from this moduli space of Hitchin system. So what? Yeah. So what do we mean by the integral structure? So there's a Hitchin map from this space to the base, certain base, space of differentials, which essentially sends an element here to the characteristic polynomial of phi. So determinant lambda minus phi, right? And it's known by Hitchin that this vibration is complex Lagrangian with respect to one of the 2,0 form defined on this space. So we have to specifically choose one complex structure out of P1 valued complex structure, because this is hyperkiller. But now we are viewing this space in different complex structure. Then what we can do is compensate one of the real equation in here and combine the other two. So we compensate real moment map equation by complexify gauge transformation and combine the other two and obtain complexify so flat connection, complexify flat connection modulo this. So this is moduli space of flat connection SLN on C. And I'm going to just state the fact that this is also space of representations of pi 1C, where this is overall conjugation. Okay, so in particular, omega I, so let me say I is the complex structure for which this interval structure is manifest. Then omega I is D to Z trace. Sorry. Okay. This is too small, right? Okay. So there, omega I. Actually, this is not very important, but I just wanted to distinguish this with omega J, which lies here. Where I define the complexified connection on C. So this is a Tucumazir form, or Holompe symplectic form, which is naturally defined on this space. Okay. Now I'll define some quantity that has to be compared with this side, this quantity in the gauge theory side, and that's we are going to think about a certain complex Lagrangian submanifold inside this space. And let's call that O. And this is space of Walpers. Well, originally I think this was defined in some filtrations of vector bundles on C, but let me just define it as a set of differential operators defined on C. So well, this part just means that these coefficients can be meromorphic at the punctures by order n. So this differential operator is defined on this space of differentials. And if you think about it, so let's say we have some Riemann surface with the punctures, and we choose a curve gamma. So there's a reference point and there's a common curve. there's an element in the pi 1c, and we start to solve this differential equation. And obviously, because of functors and genus, it cannot be globally defined. The solution should have convergence domain. So we have to, to follow this gamma, we have to analytically continue along the curves and go to the original position. And of course, the solution will not go back to itself, but it has monodromy. And by the monodromy, we define an element in here. So it's going to be inside the flat connections. And this submanifold turns out to be complex Lagrangian with respect to this omega j. So this is the definition of operators for me. Okay. Then, now to have to describe this space, let's choose certain Darboux coordinate system. Which means omega j can be expressed in this form. The wedge of the alpha I and the beta I. So alpha and beta form a certain coordinate system on this space. And since this is complex Lagrangian, if I restrict to, this is 0. And this implies locally a function S such that for all I, this holds. So this function S is called generative function for complex Lagrangian submanifold. In this case, this is generative function for all pairs. So this is the geometry quantity that we are interested in. And now the statement of No, I mean, this is specific relations that, we have restricted to O so that it's 0. I mean, if I think of another complex Lagrangian submanifold, this LS will be changed to something else. I'm sorry? Yeah. We choose a coordinate system. Since this is complex Lagrangian, this is 0. This just implies locally there's a S alpha. So we've already chosen O and the local coordinates. So the statement of NRS is this quantity W. Well, for the rank 1 case, I think omega j is something like dq du, where I think we can find this coordinate system where one Darboux coordinate spans the direction of the upper, and q is the orthogonal direction. I don't know whether this is fully satisfactory. The claim is that there is a certain, there is a certain Darboux coordinate system which this W tilde is equal to this S. So we have to, so the meaning of this inequality is that on the left-hand side we have purely gauge theoretical quantity which governs the low energy dynamics of Pauli n equals 2 theory under some omega deformation. On the right-hand side, this is something purely geometric defined on this space. So it makes the connection on the left two components. Okay, so this is the conjecture, and now we are going to see how it's proven. And let's fix the example. I said the simplest the main example will be the 4-puncture sphere. But there's an even simpler example. So first, as an exercise, let's do 3-puncture sphere. We can explicitly write this space so let's choose a curve like this, G0, G1, and G infinity. I'm sorry? C is P1 minus, sorry. So for each non-trivial loop, I just draw these loops, the element in pi1c. And we can just think of it as Gi, each Gi in SL2. And obviously, they cannot be all independent because if I just go around, it's just contractible. So G infinity, G1, G0 is 1 in SL2. And also, I want to fix the monodromy, the conjugacy class of each. And overall conjugation. You can just do the dimension count. 3 times 3 minus something something. And the dimension is just 0. And so what is the element in here? Actually, there's an upper representation of this element. So we can write a differential operator where these delta parameters are completely fixed by requiring this conjugacy class requirement. Because this trace GI knows about the monodromies of the solutions in the language of deltas. Deltas are completely fixed once we fix this trace. So there's no moduli, there's no degrees of freedom, and this is just one point. And you may recognize this is the differential operator which defines a hypergeometric function. So, and this is called hypergeometric operator. Okay. And now, then what's the corresponding thing in the gauge theory? We correspond to actually two-dimensional. Equals to 2, theory with U1 gauge group 2 So we can think of this two-dimensional theory with this supersymmetry with the gauge group U1 and this this matter multiplets. It will be a surface defect in our 4-dimensional theory, so you shouldn't confused. This will be certain 2-dimensional theory on the top of the 4-dimensional theory. We don't have the 4-dimensional theory yet for this example. When we talk about 4-puncture sphere, we will start to see the 4-dimensional physics. But here, we are only dealing with certain 2-dimensional theory. Well, we can also compute this partial function on the 2-dimensional omega deformation, and it localizes onto the moduli space of vortices. What I'm trying to say is that that thing exactly solves this equation. it can be viewed as, in physical point of view, it can be viewed as twisted chiral ring relation on the omega deformation, if it makes sense. So this two-dimensional theory has twisted chiral operators, and they form certain ring equations, and that ring is called twisted chiral ring. On the two-dimensional omega deformation, it becomes, from the polynomial equation, it's promoted to this differential type equation. I'm trying to say this is exactly the twisted chiral ring equation for this theory. So for that was for three-puncture sphere. And yeah, once I'll tell something about that when we do the four-puncture sphere. So we had now four-puncture sphere. Just a reference point. And similarly, let's give this element. And we can similarly write the moduli space. It's very similar, other than we have one more element. So if I go around everything, it's contractible, and I fix this conjugacy class. I want to now say very specifically. So I just wanted to be very explicit, so I just wrote down all the traces. You can just think of these m's as the eigenvalue of these g's. It has some weird subscripts. You may think this is very strange, but when we have many punctures, actually this is more natural, so I just didn't fix it. So eigenvalue of g0 is, for example, m minus 1 and its inverse, and so on. Trace G0, I wrote M.
Sorry, I mean, like, can you give us a hint as to why you picked -1, 0, 2?
Well, it's a convention, but okay. So for many punctures, when we have R plus 3 punctures, it corresponds to U and R gauge theory. So we have here R equals 1. So that's why we have SU2 or U2. And it's convenient to start from -1 to 0 up to R plus 1. Yeah, well, it doesn't really matter. So we start from -1, and so eigenvalue of G0 is m minus 1 and its inverse. Okay. We can do the dimension count too, in this case. I'm sorry? Yeah, I set dimension 0. Here, in this case, the complex dimension is 2. It's just algebra. So now we want to, since this is the dimension is non-zero, we want some coordinate system on it, right? I want to define A, B, and C by some trace invariance. A is trace GQ G0. This is G infinity G0. And this is GQ G infinity. So you can just visualize them as the loops which wraps, for example, this two punctures, right? So I call this A cycle. B is G0 and infinity, so it's this cycle. And I call it B cycle. C is not independent, actually. So you can check that there's a relation satisfy these 3 functions defined on the moduli space. -4 dot dot dot, which depends on, or which has some complicated dependence on these n parameters. So in particular, this space is some hypersurface in C3, the space of ABC. So it's some 2-dimensional hypersurface in C3. And also, we had this omega j, the symplectic Takuma-0 form, and the Poisson structure given by that can be represented in a very convenient way. So let's say this function is W, not W, G. Then this is given by this. Okay. Now we see that A and B nor C are double to each other, so they don't form double coordinates. But we want the double coordinates. So I will give you the double coordinate which has to do with the correspondence that I talked about, and it's actually, so it was defined in the paper by Nikita with Rosalie Charashvili. So it's called NRS coordinate system. So it's defined by saying A is a hypercosine, saying B is very complicated, okay. Maybe it was not a good idea to write this down, but Okay, finally I finished. Alpha and beta are double coordinates here. So alpha and beta, they are defined by this relation with A and B I defined here. So okay. So this is the coordinate system, double coordinate system, which is compatible with the Pence decomposition of the Riemann surface. So I want the Pence curve to be the eigenvalue of the holonomies along the Pence curve to be my double coordinates, half of the double coordinates. And we properly find the double pair of that by doing some algebra. Yes?
So all the ends were only defined up to replacing them by their reciprocal.
Mm-hmm.
So how does the formula for theta change? Replace the I by n?
The formula will not change, I think. I mean, we already see many symmetry here, and
It's hard to see.
yeah, that's true. Okay. So this is the double coordinate system that we want to use. Oh, and I didn't write the upper for this. So inside this two-dimensional complex two-dimensional space, we are thinking of a complex Lagrangian submanifold, which is spanned by the differential operator. This is very similar to the hypergeometry case. Now, this is something similar to the hypergeometric operator. Again, these delta parameters will be controlled by various combinations of this M. Because again, this controls the holonomies of GIs, or the GIs. So they are completely fixed once we fix the M's. But we have a free parameter now, which is H. So we can visualize this space as some two-dimensional space, perhaps with alpha and beta. And those differential operators spans one-dimensional submanifold inside. Maybe alpha and beta. No, it's not very good. But anyway, it's a one-dimensional submanifold inside. And we see that this H direction spans this space of opers. And actually, so we have the other orthogonal direction given by the varying degrees Q. But we are fixing a Q, so it's a direction that's orthogonal. Okay, so this is the opers. Okay, I have like 15 minutes. So now the goal is to construct or engineer these opers from the gauge theory point of view. 4D n equals to theory with the surface defect that as I told you just before. Yeah, that's right. So how do we engineer the surface defect? I think erase it. I erased the 4-puncture sphere. So now we're going to insert the surface defect here with position Z. Remember, we are thinking of the 6D origin compactifying on this Riemann sphere to make the Fourier equals 2 theory. Our surface defect will be certain defect which wraps 2 out of 4 dimensions in our spacetime, but located at this Z here. In the M theory picture, it will be an insertion of M2 brane, a single M2 brane, located at this Z. And it can be the Nekrasov partition function can be also computed for this 2D fully decoupled system. And by the way, so the surface defect is defined as a low energy. So surface defect is defined as a low energy defective theory living on the M2 brane or 2-dimensional surface. But it's coupled to the bulk Fourier equals 2 theory because the theory on 2D has certain flavor symmetry, which can be gauged by the bulk gauge field, gauge symmetry. That's how they couple. And we can do the partition function computation for these theories too. And at this point, okay. So other than Q, we also have this Z coming into the partition function. And I just have to say that it boils down to a summation over Young diagrams, set of Young diagrams with this kind of measure. So there's a box counting parameter Q. So Q comes in as a box counting parameters for Young diagrams. And there will be some measure for each lambda properly defined for our n equals 2 gauge theory. But because of surface defect, we have an additional contribution. And some very complicated term, which I don't write. If I don't have this term, this will be just 4n equals 2 gauge theory partition function without the defect. Now, also, if I just take the limit of Q going to 0, turning off the bulk gauge coupling, I'll have just vortex partition function of 2-dimensional gauge theory without the coupling. But now we have some complicated combination of those two. So the coupling between 2D and 4D system is encoded in this complicated term. So this whatever term defines both K and this Young diagram lambda, and all the equivalent parameters. No. Yeah, right. This partition function is supposed to be well defined around 0. So we can safely take Q equals 0. But if you think about it, this is first. I mean, this is defined as a series expansion in Q, almost by default. So you think about for each K the instant moduli space, and then do some equivalent integral over it. So it should be in this form.
So is this defined
q equals around q equals 0. So as these pictures suggests, maybe I didn't say it. We're in the regime where q is less than 1 and larger than 0. And that's the same to say we are choosing a Pence decomposition of the Riemann surface, and that's also the same to say we are choosing a weakly coupled regime to do the gauge theory computation. Weakly coupling regime. Pence decomposition of the Riemann surface corresponds to choosing weak coupling regime. Okay, so in those two limits, we just recover 4D, purely 4D, purely 2D, but this is some combination of those. And now we take, as promised, with this limit, and do and see the asymptotics of this function.
This is about distance on this orbit. So which supposed as some kind of connection, they have a monitor and divisor.
Yeah, I think that's what's happening. So because we have the two-dimensional defect, it can fractionalize.
This integral is over, for you would be like 1 to the power more extension 1 to 5. That gets the Z vector for you. Oh, you have that. Z vector or just one number?
Z is a vector. I was going to say that. There's a choice of this M2 brane where it is placed in the low energy. I was going to say that. Okay, in the epsilon 2 going to 0 asymptotics, we're going to have some singular contribution, but because I also didn't say, we are aligning the surface to be on the epsilon 1 plane, not the epsilon 2 plane, where epsilon 2 is going to 0. The singular part will only come from the bulk contribution, which is the same as this W tilde, which we have seen before. But now we have the regular term, which I call chi, and all the dependence on Z too. And we have subregular terms. But anyway, the point is that this surface defect contribution modifies the regular term. Without this term, we had 1 here. But now, with this contribution, we are modifying our regular part in the asymptotic selection to going to 0. And what I haven't told you is that in the low energy theory, I have to choose where. So we are thinking of the Saebyeok curve, which is the branch coupling of this Riemann surface. I have to choose where I put this M2 brane. So actually, this is a vector beta, where beta goes from 1 to n. So we have n of those. So n is the choice, my surface defect. Oh, n is which started from a n-1 series type of 2,0 theory on 6D. That choice is still here. So I said I only deal with A1 case, which makes n equals 2. So we have 2 choices here for my example. I compute chi by taking the limit. I can also compute the W and chi at the same time. So we put.
Is there a formula for chi?
There's a formula for this thing. I didn't write this, but it's something very concrete. Also, I didn't write this thing, but it's something very concrete. Even there's we can computer code it. So, Right, so I told you about the subsymptotic behavior and epsilon 2 going to 0. And why we are doing this? Because now I want to make a connection with this operator, right, apparently. And for that, we need a QQ character. And I think I won't write what it is. So QQ characters are certain gauge theory observable, half BPS gauge theory observable, local in 4D n equals 2 theory. And it has some auxiliary variable. Sorry, maybe I shouldn't use chi here. Let me call it psi. And my chi is now a QQ character. And it has some auxiliary variable x. And while I don't want to tell you how it's constructed, but it has some nice property. I can tell you it has some nice property that its gauge theory expectation value is regular in X. And this turns out to be something very non-trivial. It imposes certain constraints for our partition functions. So we can pull out some useful analytic information of this partition function using this property. More specifically, what I'm practically doing is that pulling out the negative powers of this expectation value. X is, you don't see X here. Sorry. There's a physical meaning of X, but then I have to go to the string theory construction of the 4D n equals 2 theory. So I would rather not mention it here. It's a complex number. It's a formal parameter, which is a complex number. And chi is an observable which has that auxiliary variable. That has which has nice property, which where the gauge theory expectation value is regular. In other words, the negative power, if we just pull out the negative powers of this expectation value, it's 0. And this turns out to be very useful to derive some analytic properties of this partition function. So at the bottom line, what we get is the following. Okay, I can just erase this, I think. At the bottom line, we will have an equation satisfy that thing. certain differential operator acting on Z 2D 4D. And this is 0. That's the consequence of this. Okay. This already looks very similar to the operator. So what I'm really doing is taking this limit to this equation itself. And that becomes this equation. Yeah. Thank you. Maybe I didn't explain those parameters. Here we have capital deltas, which is determined by the masses of the hypermultiplet. Those deltas becomes this small delta in the limit of epsilon to going to 0. So this delta is completely determined by the gauge theory data, which is the mass of the hyper. And other parameters are just all the gauge theory parameters. Q, the box counting parameter entering here. Z is also, it has some 2D gauge theoretical meaning. Epsilon 1 and epsilon 2 are the equivalent parameters. So what this tells you is that we constructed the operator, but now everything is in the gauge theoretical data. Deltas are masses of hyper. This H is now coming from this term, and H turns out to be the gauge theory expectation value of this chiral operator in the limit of epsilon to go into 0. So if I make a remark about the quantum Hitchin system, by the beta gauge correspondence of Nikita and Samson, this thing has to be something knows about the quantum spectrum of the quantum Hitchin Hamiltonian. And we see that it is also H, which is the coordinates on the space of Wolpers. So that's the connection with the flat connections with the quantum Hitchin system. And yeah, and also, not only these H or delta parameters, we also have this solution psi, because now we can construct solution psi as by taking this epsilon to limit to 0 limit of this object. So we also have this solution psi. But it's a solution in specific convergence domain, because we have chosen, when I wrote this expression, I secretly chosen the convergence domain here, roughly. So L region is 0, Q, so 0, Q, 1, and Z. Z is larger than 1. So what I'm trying to tell you is that we can similarly engineer the operators in other convergence domain here and here. So let's call it M and R. So R will be 0, Z, Q, 1. M will be in the middle, 0, Q, 0, yeah, 0, Q, Z1. We can engineer the operator in the similar way, and we get the solutions at each patch. Now the question is, how do we analyze? We have to analytically continue the solution from here to here, here to here, because we want a B cycle, right? So we have to know how this partial function analytically continue from region to region. So that's the final part. So this was Z, 2D, 4D, and beta. it turns out that we can represent this partition function as a contour integral. With some auxiliary variable x. So this integrand is completely determined this thing, which I didn't write. But we have introduced some auxiliary variable x, and it's a contour integral in x. How does it look like? It looks like the following. So in the space of x, the poles are like this. They're all simple poles, by the way. So one rays of simple poles goes to the right, so to speak, goes to the right. And there are n rows of poles, or in this case, 2 rows of poles, semi-infinite rows of poles going to the left. And our contour C is exactly separates these 2 kinds of poles. Now, it can be shown that this integral uniformly converges, and the integrals are well defined. Then, how do we recover this series expansion in Z inverse? When Z is larger than 1, we can close this contour like this. And it can be shown that this integral over the semicircle converges to 0 when this holds.
Can you say again where you got this contour integral? I don't think I followed.
So practically, we just looked at this expression. It involves a bunch of gamma functions. It has a bunch of gamma functions on the numerator and the denominator. And then we use our knowledge of the simple poles of the gamma function and so on.
Okay, so you saw a bunch of gamma functions.
Yeah.
You said, that's like a
Yeah. But there's also physical meaning of this contour integration in the 2D physics and surface defect. But let me not mention that. Anyway, the point is that we can manipulate those gamma functions to express that in this form. And we didn't have to add this semicircle because this integral is already well defined. Now I'm just adding this 0 contribution in this regime only to evaluate this integral by the residue theorem. So we choose this semi-infinite poles on the right to recover this form. But that's when Z is larger than 1. So what about Z is less than 1? We can instead choose the contour on the left. And of course, given this condition, it converges to 0. And we now have 2 rows of contributions from the residue theorem. So it can be written as gamma, sum over gamma from 1 to 2, C beta gamma, Z, let's say M gamma. So I call C beta gamma the connection matrix. It connects the solutions in two different regimes. And it's 2x2 matrix. So we have gone from here to here. Similarly, we can go from here to here. Going around the punctures is not difficult because it's something given from the beginning. So we can just concatenate those analytic continuations to compute the solution, to compute the analytic continuation of the operas. The important fact is that in the limit of epsilon 2 going to 0, this produces oper. So the monodromy of operas can be obtained by taking the monodromy of this thing, by applying epsilon to the 0 limit to the monodromy of this thing. So the conclusion is that by doing that, our A cycle, you can imagine that A is not difficult. It lies in a single convergence domain in M. So A cycle is not difficult. So A is just given by this expression where A is a Coulomb moduli, the equilibrium parameter. And now B is very complicated expression that I wrote to you there. But there beta was unspecified. But by doing this computation, what we figure out is beta is d alpha, dw d alpha. That means beta, this exactly, from the definition of the generative function, this just tells you w is s and this coordinate patch. Okay, so that's all for my talk. Thank you. Yeah. So what we have seen by the analytic continuation of this partition function is move from here to here, and also here from here, right? By concatenating those analytic continuation, we can construct the monodromy operator for this. But I have shown you that in the epsilon 2 to 0 limit, this produces the solutions to the operator equation. In the epsilon 2 to 0 limit, it has some singular part, and the regular part, psi is the solution to the operator equation. So what I'm doing is to compute using this kind of contour integral, compute the monodromy along this curve for this thing, but then taking epsilon to 0 limit. Yeah, so it's defined in certain patch in the convergence domain. You see that this is expanded in Z inverse, which has to be, so it's in this domain where Z is larger than 1. Similarly, so in other words, to go to the other patch, we have to analytically continue the solutions, or in this case, the partition function. That's what's happening here. But obviously, the basis of the solutions do not match with each other. It goes just 1 to 1 or 2 to 2. There's a matrix which mixes up, and that can be computed by this analytic continuation. So by taking products of these matrices, we can compute the monodromy, and that computes the monodromy of the solutions to the equation of operators. That's right, yeah. What happens to psi is obtained by taking epsilon 2 to 0 limit. And this is the consequence. A cycle is easy. A cycle only lies on the region M, so it's easy. But B cycle is more involved, and the result is this. So this is very complicated. I have shown you how B is expressed in alpha and beta. But the result of this computation just exactly matches with this. There, the beta was unspecified. Now, what I'm saying is that for the operators, if we restrict to the operators, we have to restrict by this. We have to restrict beta by this. That means W tilde is S. So, sorry, maybe I wasn't very clear. Here, this beta runs from 1 to n. In this case, 1 and 2. So that produces two solutions. And this is 2 by 2 matrix.
What's the generality? Which generality is out?
So I've done the explicit computation for SL3. For obviously the Lagrangian case, because we are doing the instant counting, we have to have the Lagrangian theories. So it cannot be directly applicable for 3 generic punctures, for example. So in that case, we have 2 generic punctures and 2 minimum punctures. I think this can be more generalized to many, many minimum punctures with 2 maximum punctures. And also for the higher ranks. So whenever it's non-Lagrangian, there's no instant accounting. It's difficult. Maybe the dictionary has to be reversed. Maybe we can compute in the geometry side because the upper is still well defined with those singularity behavior around the punctures. So if we have 3 maximum punctures, I mean, the singularity behavior is still well defined. Hessian system is well defined. So this upper is well defined. And we can compute something from the geometry side and maybe talk about something about the field theory, but that hasn't been done so far. So this just means at the level of the flat connections, we are looking at the monodromies on the punctures. For higher ranks, this notation means it's maximal. In which sense? In the sense that the eigenvalue of the monodromy around this puncture is maximal. So, right, all distinct. It has n-1 degrees of freedom because it's SLN, right? Minimal means they are all identical, maximally identical. No, because irregular singularity typically corresponds to non-Lagrangian theories like Algiers-Douglas theories. We lose the control like instant accounting, instant partition function there because we don't have the gauge theory description. I mean, it's hard to imagine what we are talking about by saying instantons there. I mean, there's no gauge field. So what I was telling to Andre was that maybe we can just start from we reverse the dictionary, start from the geometry, because geometry is just well-defined there with the irregular punctures, compute something there, and go to the gauge theory and figure out what it means in the gauge. Sorry, not the gauge theory, field theory side. Yeah. Thank you.